All right, today we're going to talk about scale changes, so you're going to want your note card out again. We focused on specifically translations and talked about a translation rule, and today we're going to talk specifically, very similarly, about scale changes and how they work in the equations using that generic function and some different parent functions. So what I'm going to have you do to start out with is try this first problem before we get to algebra with specific equations. It says, here's the parent function, y equals x squared. Chose that one because you know quite a bit about it. And just complete the table with the 5 points that I gave you. Then what I'm going to have you do is double those x values, so you'll just double those, and then triple the y values that come out of the equation. When you're done with that, your job is to come up with the equation that fits this table. Okay, I want you to pause the video and try that for me. Okay, this may have been a little bit challenging, okay, but I want to relate it back to what we did last class with all of our transformations with Purple Note Card. Okay, a number out front is a scale change related to the vertical axis. In the case of this one, multiplying by 3 is a vertical stretch. But if you look at your note card on the inside, if you have the situation where you're taking the x values and double them, that's like taking this -2, I'm going to use the positive one, but this +2, multiplying it by 2 gets you to +4, and that's a horizontal stretch. But if you put 2 inside here, that doesn't follow the pattern of what the note card says. And the note card says that when you have a b value between 0 and 1, that's what makes a horizontal stretch. And it's opposite of what you see, just like we talked about last class, because really this is saying 1/4 x squared times 3, 3/4. It's talking about the vertical stretch or compression always, because we're simplifying to find y. So if we want to talk about specifically just what's happening to x, excuse me, just what's happening to x, it is opposite of what we see, kind of like what we did with translations. Okay, so to simplify this as we go through here, all we're going to have to do when we're given this rule is keep the y the same. We'll put it out front because we know vertical is what affects y. And then inside, whatever is affecting x, we'll use the reciprocal, because that's the opposite operation. This says times by 2, this says divide by 2, or multiply by the reciprocal 1/2. Okay, so let's practice with some parent functions. I used the same one on the first example to tie it into what we just talked about. But how you'll set these up is you'll write y equals, and then you'll leave a little space, parentheses where your parent function is, and then square it. So I know there's going to be a number here and a number inside with x. So with y, we see 1/3, that stays. Whatever you see with y stays. And then we're just going to reciprocate what we see with x here, so that'll change to it too. And anytime we can with our parent functions, we want to simplify. In the case of powers, we can simplify. Order of operations tells us do those powers first. So that's 4x squared multiplying by 1/3. And then straight across, if it helps, think of that as 4/1. We've got 4/3 x squared, and that's it. Okay, so this next one is a cube. It acts the same way. Okay, we're starting with a little space in front. Grouping symbols are just getting cubed this time. And our number in front is what goes with y, so that's -4. And then we reciprocate, call that a 5. Okay, powers first. 5 cubed is 125. X cubed comes down. And we're going to multiply that by -4 for a -500 x cubed. Okay, so it's to say when we multiply the x values by 5th and multiply the y values by -4, in the case of a cubic, what that really does is reflects over the x-axis, which makes sense here. The y value went from positive to negative. That does reflect over the x-axis. And then multiplies by 500 when it comes to the y's. That seems a little crazy based on this, but remember that parent function is getting cubed, which is why it's getting large so fast. Okay. Next one is a root. And honestly, this is one of the more challenging parent functions just because sometimes simplifying with roots can be a challenge. So let's look at how this one shows up. The number in front for us is 4. We're having a root symbol. Remember, leave some space in front. When we see a 5x, we'll write 1/5x. Okay? And for the case of this, the only thing you're going to do to simplify with square roots is first, can you take the square root of the number? We can't take the square root of 1/5, but I want to talk about what happens when we look at the square root of 1/5. From algebra, square root of 1 over the square root of 5 is how we really simplify, and that's 1 over the square root of 5. And hopefully you remember that this is a problem. Okay, we can't leave that square root in the denominator. And traditionally, what you were told to do is multiply by whatever you see on the bottom. But the reason you were told to do that is because now I have the square root of 5 over the square root of 25. Our goal was to get rid of the square root underneath, and now that the 25 is showing up on the bottom, that's a perfect square that simplifies, and we just call that 5. They cancel each other out, essentially. Okay. But what we're going to do is take that same kind of idea and just shift it slightly. So the first thing I want you to do is rewrite it. Instead of 1/5 times x, we talked about this on the first example, is these were opposite operations. This had 5 times x. I'm going to have you write this as x divided by 5. Means the same thing, so that's like 1/5 there. But the reason I'm having you write it this way is to simplify what we're going to do next, okay? So we're going to rationalize, still 5 over 5, but the square root symbol already exists over this whole thing. So what I'm going to have you do is just extend it out a little bit and put a 5 over 5. And these things are valid because anything over itself is just 1. Multiplying by 1 doesn't change the value of the expression. Okay, but now we can simplify across, and it makes pretty easy and pretty clear what goes with what. So that says 5x and over 25. And that bottom part simplifies just like it did with a regular 1/5. So we've got 4 times 5x, and then over just 5. Last thing I'm going to have you do, since this is our grouping symbol now from the original, we're going to move this 5 over to the side with the value that goes out front, since it's no longer included in the root. So your final answer is y equals 4/5 square root of 5x. So you won't always have to rationalize. This happened because we had a fraction underneath. Okay, if we start out as a fraction here, it reverses. So remember, the only time you simplify in those cases is if that thing is a perfect square. Okay, next parent function, we've got our exponential. Remember, for exponentials, the number has to be included in the parent function. It is, but our x is in the exponent this time, so that's where we're going to leave some extra space. A little bit out front like normal, then the 5, a little bit in front of the x. So to start with, our 7 goes in front. We're going to put a times or some parentheses to indicate that those are separate, doesn't look like a 75. And then instead of 3 over 2, we'll flip that to 2 over 3. Now, in the case of exponentials, okay, these cannot simplify, because order of operations tells us we have to do exponent first, and the 5 is the only thing being raised to that exponent. As soon as you multiply these together, then it says 35 to some power, and that is not what the parent function indicates. Okay, so these ones you will never simplify, okay, which means that the most straightforward when it comes to scale changes. Okay. I'm going to have you try number 5 and 6. Pause the video for those, and then we'll talk about them when you get them finished. This one was a little bit tougher, but if it helps, call this 1x over 5. So then we see 1/5. Now what's really important is we are writing this wherever we see the x, that's where our extra number goes, is just in that part. So this 1 has to stay. So when we write this, -4 goes out in front, just like we have been doing, and that's 1 over. Instead of 1 over 5, it'll be 5x. And just like we have been doing, we're going to multiply straight across, call that 4 over 1. So it's -4 over 5x. Remember, with this parent function, thinking about your purple note card, If we have a reflection of the x-axis or a vertical something, that's going to show up on top, and it comes from exactly this. They just simplifying, we can take 4 times the fraction, and that ends up putting that number on top. Okay, this one wasn't so bad because it was a cube root of a number 9 that wasn't a fraction, no problem, and 9 is not a perfect cube, so we can't simplify past that. What we're going to do now is go backwards. So this one is asking for the rule. So it's going to look like f of xy equals some number in front of x, some number in front of y, and the same rules apply. Okay? We want to see y equals some number in front, and that number in front goes right here for y, exactly what we see. And then in the grouping symbols, we'll see some value in front of x, and we will use the reciprocal. So the only problem with this number 7 is that we don't have y by itself. Okay, so we'll multiply that 7 over, and because we know that number is supposed to show up in front, that's where we'll place it. Okay, again, if it helps you put a 1 here, so that says 1/3, so when we write our rule, we have to flip that to 3. So our rule looks like 3 times x, 7 times y, and that's it. For these ones, you don't want to simplify with the pattern because I didn't ask you for the simplified equation. All I wanted on this one was the rule, and this form actually helps me do that. Okay, over here, f of xy equals, we only see a 5, 6, there's not a number out front, so we'll change this to 6 this, and we'll just leave y alone. If it helps you to write a 1 and put a 1, that's great. But there really wasn't a scale change here because multiplying by 1 does not change the value. Okay, so these ones are going to be very similar. Remember, if you don't see grouping symbols, you want to add them in right around the x. And then that tells us that this really goes with the y when we write our rule. So nothing with x and -8 with our y. And this is another one where it doesn't say y equals, so we have to multiply that 6 over. So it's y equals 6 times the square root of 2x. So then our rule is scale change for xy is 1/2 x, flipping this part, and then 6y. These ones are going to be similar. The only thing is you'll notice on these ones you'll see there are 3 places that have numbers involved, and we only have 2 places in the rule. So when we move to get y equals, we have to make sure we know where it goes in order to simplify. And these are the only cases where you have to simplify before finding the rule. So this one, that 3 goes in front, just like we have been doing, but we've got to multiply that through to be able to write the rule. And now, reminding you that this is the parent function 1 over x, the number with x in the bottom goes with the horizontal scale change. So when we see 4x, we'll write it as 1/4 x, and then that 15 has to be the part with y. And there are other ways to do this, but this is the way that matches most directly to when we go the other direction. Okay. On number 12, you'll see this weird f. If you look at the next problem, this is an example of something that's just written as y equals f of x. It just indicates that it's not one of our regular parent functions, but it's still a function because it passes the vertical line test. Okay, so when that's the case and there's not a simple equation to write it, they'll just use this f of x notation. So these parentheses act the same way any of our other grouping symbols with our parent functions work. It's going to be very similar to the last one. Okay? With that in mind, try this one, write the rule, pause the video, and then you'll check it. You should have gotten 1/7 x. And then when you move that over, it's going to make it 3/4 y. going to talk about how we use these rules to graph. Okay, so right here, they gave us the equation of a scale change that was happening, and we're going to go ahead and rewrite it with that 3 where it's supposed to be. And this says we're going to take the x values and do something to them, and we're going to take the y values and do something to them. This is an equation, which means it's related to your purple note card, whereas the rule is directly related to the graph. So what I want you to do below here is make a big table. And it's not going to look like a normal table of x and y values. Instead, the left-hand side is going to talk about your original points, and the right-hand side is going to talk about your scale change. And usually you won't even need this part, but I want to write it in the way that you're used to seeing. Okay? So when we look at this 2x, we'll flip that to a 1/2 x. And this 3 stays. So on your note card, 3 is a vertical stretch, and 2 is a horizontal compression. That's because you're taking the x values and multiplying them by 1/2. So I want to emphasize again, just like before, with the translation, the rule is directly related to the graph. It tells you exactly what's happening. Nothing switched. Okay? We talked about multiplying by 1/2. That's going to crunch it inside this way. Multiplying by 3y is going to pull it both directions and stretch it out vertically. Okay, so all we're going to do is pick some points on here. And these ones were picked for us. But in general, when you see a graph, what you want to take a look at are any endpoints or any turning points. Okay, you'll notice that the x-intercept, in this case the y-intercept was, but the intercepts aren't as important. And that's because under a scale change, an intercept where part of it is 0, the 0 is not going to change. Okay, where it lands on the x-axis will, but not necessarily the 0 itself. Okay, so what we're going to do is just label these ordered pairs. A is -6, 0. B is -2, -2, and so on. And labeling them just kind of helps us figure out when we connect them how things work. Because in this case, we know our shape's going to end up the same because we're just scrunching it this way and pulling it this way. But sometimes in your rule, you're also going to have reflection, and it just kind of indicates what's supposed to connect to what. Okay, but we're just running it through this rule. And what I usually do to save a little bit of time is do all the same operation at once. So instead of finding each point one by one, I'm going to find all the x values first, because I know I'm taking all the x values and multiplying them by half. So half of -6 is -3, half of -2, -1, and then all the way down just following that same pattern. Okay, so on the y values, we're just tripling everything that's in the second column. So remember, 0 stays 0. Everything else is going to stretch out. And then we can plot these new points. And what I'm going to have you do is add the notation that should be familiar from geometry, is this little prime. And that just shows you it's the result of the transformation. So remember, the vocab reminder, the result of the transformation is called the image. So this would be the image of the point. And our whole thing would be the image of our y equals f of x. So plotting these points, they gave us a scale this time. I will tell you that sometimes I give you a graph that doesn't have any labels on it. And that's just because sometimes when you do a scale change, the numbers are wildly different, and there's no guarantee it's going to fit on the same graph as the original. So in those cases, be sure that you pick a scale that's appropriate and let me know what that scale is. Okay. We're going to connect them in the same way it started. So A goes to B, B goes to C, C to D, and D to E to finish it. Okay, so here we saw horizontal compression and a vertical stretch, just like our equation and our rule stated. Last two are pretty straightforward as long as we understand what a rule does. And remember, a rule is directly related to the graph. So this asks you for the scale change s. That's our rule. It started out as of xy. And we want our rule to say that we're stretching the graph horizontally by a factor of 4 and shrinking it vertically by a factor of 1/5. So we know horizontally means that 4 has to go with the x, and vertically means that 1/5 has to go with the y. But remember, the rule is directly related to the graph. And when we use the language like horizontally and vertically stretched bars, it's talking about what's happening on the graph. So we're not going to change anything here. Horizontally by a factor of 4 means literally 4x. We're multiplying those things by 4. Same thing, vertically by a factor of 1/5 means it gets smaller. We're going to put 1/5 in front of the y, and that's it. Okay. Next thing, in the last problem here, just says the zeros. Remember, zeros are the same thing as x-intercepts. The x-intercepts of a function are -12, -48, and the y-intercept is 16. So you remember, a function can have multiple x-intercepts, but it's not possible to have more than one y-intercept. I do want you to think about these as ordered pairs. It's going to help us for the rule. X-intercepts are something 0, and y-intercept is 0 something. And then we're just going to plug it in this rule, okay? Because under a transformation, it tells you exactly what to do. It says take 1/4 and multiply it by the x values. Our x values are x-intercepts, so let's label x-intercepts. And we're just going to plug it in. -12, 0. This part gets multiplied by -12, and anything times 0 just stays. So we've got -3 for the first one. Make sure it says an ordered pair. Next one started out -4, 0, but times a 4, -1, 0. And then 8 times a 4 is 2. The y-intercept goes the same way. We're taking it, and this 16 is the only part that matters, so we're taking that times -2, turn 0 into 32. Okay. One thing I want to point out for your homework, there's a vocab term called size change. So add this note here. A size change is where we look at our rule, and here's the general function, or general rule part, and this is on. It might not actually be on your note card, but here's why I didn't put it on there. This A and B are not the same A and B as your purple note card, like for the generic function, and I didn't want to confuse you. Okay, but I'm putting this little notation here. A size change is when you have a scale change that affects the x-axis and the y-axis exactly the same. Basically, you have to see the same numbers here. So this could be a 4x, 4y, or any variation of that where these numbers match. Okay, so you have one question that asks about a size change, and that should be helpful for it. If you have any other questions on the homework, as always, feel free to come in to ask questions.